In this video, we're going to see why is e the base of natural logarithm. And you must be knowing that the value of e is 2.71828 and so on. So in other words, we're going to look at the question, why is 10 not taken as the base of natural logarithm? And why is this particular number taken as the base? So let's start. You must have seen a scientific calculator, and over here you must have seen log written as one of the log buttons and ln written as another log button. So the common logarithm is the logarithm with the base 10. It is either written as log x to the base 10 or simply as log x, as you can see on the calculator, while the natural logarithm is the logarithm with the base e, and it is either written as log x to the base e or simply ln, which is natural logarithm of any number x, as on the calculator. Remember, e over here is a particular number, an irrational number whose approximate value is 2.718. Common logarithms are super useful in doing complex calculations. For example, if you want to do division or even multiplication, taking out the square roots or high order roots, and if you don't have a calculator, you can use common logarithms, the logarithm with base 10, and you can easily do all these calculations, of course, if you know how to do it. Moreover, log 100 to the base 10 is simply 2, or any 3-digit number would always start with 2 point something something something. Similarly, log 10,000 to the base 10 is 4. Remember, we are talking of the common logarithms right now. And it's very easy to understand that a 5-digit number would start from 4 point something. So the number of zeros over here is 2 and over here is 4. So this is very easy to understand. While log 100 to the base e is 4.6051 and so on. While log 10,000 to the base e is 9.21, which is so difficult to understand. So if you don't have a scientific calculator or a log paper, you won't be able to even find this out. So the question is, then why do we take e as the base of natural logarithm? Why is this particular number taken as the base of natural logarithm? What's so special in this odd-looking irrational number that mathematicians have decided that we need to take this as the base in calculus? Why don't we simply take common logarithms in calculus? Or, in other words, what's so natural about these natural logarithms? Remember, natural logarithms always have the base e. Now, if I say log x to the base b, this is nothing but the inverse function of the exponential function b raised to x. Similarly, log x to the base 10 is the inverse function of the exponential function 10 raised to x. Remember, exponential function and logarithmic functions are inverses of each other. Similarly, natural log of x or log x to the base e is the inverse function of e raised to x. So there must be something special about e raised to x, so that the mathematicians have decided to take log x to the base e and not any other number. Now, in this video, from now onwards, if I just say log x with no particular base, we are going to understand that we are common logarithm. Why? The natural logarithm will be written as ln of x. The concept of e raised to x has its origin from a classic compound interest problem. Suppose a principal of $1 is put in a bank and the bank pays 100% interest. Of course, no bank would be paying that, but just consider it for a short moment. How much money will you get after a year? Well, it depends upon how many times are you going to get the interest within a year. So how much money will you get if the interest is compounded after 6 months? Means it is compounded 2 times a year, which means that after every 6 months, your interest is accumulating in your account, and then you get the interest on that interest also. And how much money will you get if the interest is compounded every month or 12 times a year? And how much money will you get if the interest is compounded every day, 365 times a year, and every second? How much interest will you get if the interest is compounded continuously, infinite times a year? So if it is compounded annually, we know that principal is $1. The rate of interest is 100%. Of course, no bank is going to give that, but just for a moment, let us understand this. 100% can be written as 100 upon 100, which is 1. So remember 100% and 1 are same over here. And the number of years or the number of times you're going to get the interest is 1. So the compound interest amount formula is A is equal to P 1 plus R the whole raised to N. When we substitute the values, 1 into 1 plus 1 the whole raised to 1 is 2 raised to 1, which is 2, which means you're going to get your money doubled. You put 1 rupee or $1, you're going to get 2. But if it is compounded 2 times a year, twice a year, principal would still be 1, but the rate of interest would become 50%. 50% per 6 months, 50% per semester, or simply 1 upon 2. But this time the number of periods will be 2 semesters. Use the same formula, substitute in it. So this time we are writing 1 bracket open 1 plus 1 upon 2, which is the rate of interest, and 1 multiplied by it means, of course, this 2. So the answer to this is 2.25. So you're going to get $2.25. You're going to get the extra 25 cents because after 6 months you were credited with certain interest, and then you're going to get the interest on that interest also. That means you're going to get some extra money. Similarly, if it is compounded 12 times a year, we'll be using 12 over here and 12 over here, and the answer would be 2.61 approximately. So $2.61. And if it is compounded every day, we are writing a 365 in these two places, and this time we'll be getting $2.714. If it is compounded every second, we are going to get 2.7182817 something. And if it is compounded, let's say every millisecond, remember 1000 milliseconds is 1 second. So you're going to get 2.718281828415947, etc., etc., etc. And if it is compounded continuously, which means that this number becomes infinitely large, and so is this number. So we are writing limit as n tends to infinity, 1 plus 1 upon n, the whole raised to n. Then you'll be getting 2.718281828459045, etc., etc., etc. And you have guessed this correct. This number is nothing but E. So when this n becomes very, very, very large number, very big number, this number will get closer and closer to E. And similarly, we can say that instead of n tends to infinity, if n tends to 0, so instead of taking 1 upon n, we are simply taking in n. And instead of n over here, we are taking the power as 1 upon n, we'll still get the same answer E. But what if we had some other principle? Let's say we don't have $1, it could be $1,000 or $2,000, and some other rate of interest. We just generously took it to be 100%. Remember, since we took it to be 100%, since we had the principal 1 and the number of years also 1, then we got E. But the question is, what if we had taken some other principle, some other rate of interest, some other time period? Then we wouldn't have got E, isn't it? In real life, there is a continuous growth. It isn't that there is a sudden growth after a day or a month or a year. In a bank, you'll be credited some interest after, let's say, a quarter or a month or 6 months or a year. But in real life, the growth takes place continuously, just like the growth of population, the growth of your fingernails, the growth of your hair. They grow continuously, but of course, that rate is very, very less, at a very slow rate, but the growth is definitely continuous. So let's say the principal is P, the rate of growth or the rate of interest is R, and the time period is T. Then if we divide this rate into capital N parts and we multiply this time period by this capital N, we'll get this particular formula. Now what are we going to do is, we are multiplying and dividing an R over here. That is because this R upon N will have a multiplicative inverse, a reciprocal N upon R over here. We can rewrite this as P bracket open, and we have tr as the power, and within this we are writing 1 plus r upon n the whole raised to n upon r. So what we did exactly is we took this n upon r and we took the power of that as the remaining t and r. Remember, if we open this, we again get the same thing. And now what are we going to do is we are going to make this n infinitely large because the growth takes place continuously. And of course, this rate of growth will become increasingly small and small and small. So we have applied a limit. We are bringing this n to infinity. We are making it very, very big. Then we can pull out this p because p is independent of the capital N. As n goes towards infinity, this n upon r also will go towards infinity, and r upon n will go towards 0. So instead of writing n tends to infinity, we are writing n upon r tends to infinity. Now remember, this number is going towards infinity. We have 1 plus the reciprocal of that number, and the same number is written over here. So we can compare this to this formula, which is as n tends to infinity, 1 plus 1 upon n, the whole raised to n, is equal to e. So this entire thing becomes e because of this formula. We just saw that in the previous slide. So we have p, e, and e raised to tr, which can be written as the amount is equal to principal into e raised to rt. Just r is written before. So we saw that if the compounding is done continuously or the growth takes place continuously, we have this e in this formula. Now, we also know that the derivative of x to the power n is n into x raised to n minus 1. And the converse of that is the integral of x raised to n is equal to x raised to n plus 1, the whole upon n plus 1 plus c, where n cannot be equal to minus 1 because if n is minus 1, this denominator becomes a 0. But when n is exactly minus 1, this x raised to integral of x raised to minus 1, which is 1 upon x, is how much? Even mathematicians try to find the answer to this. Now today, of course, we know the answer to this is the natural log of x, but we are going to understand how did this come. Now look at this function. Limit of a raised to x minus 1 upon x when x tends to 0. Now you may be asking, from where did this come all of a sudden? Just bear with me and we are going to answer this in a moment. So let this numerator a raised to x minus 1 equal to h. So we can say that a raised to x is equal to 1 plus h. The minus 1 is brought over here. And if we write this taking logarithms on both sides, we can deduce x is equal to log of 1 plus h to the base a. So x is equal to log of 1 plus h the whole upon log a. Remember, right now, since we are writing without any base, we are assuming it to be a common logarithm. As x approaches 0 over here, a raised to x or a raised to 0 will become closer and closer to 1. And if this becomes closer and closer equal to 1, h will become closer and closer to 0. So we have this. So instead of writing log 1 plus h upon log a, we can write this as limit as h tends to 0, h. Now, from where did this h come? It came from here, a raised to x minus 1. Upon x. Now, what is x? X is log of 1 plus h upon log of a, which we have written in the denominator over here. Now, we can take this in the first line and this h in the third line. So log of a multiplied by limit as h goes towards 0, 1 upon log of 1 plus h the whole upon h. So log of a multiplied by limit of h going towards 0, 1 upon, and we are just pulling this the whole upon h outside, and we can rewrite it as 1 upon h log of 1 plus h. And now this 1 upon h is multiplying with a logarithmic function. This can be written as the power of that logarithmic function. So log of 1 plus h, the whole raised to 1 upon h. And what is this equal? As h goes towards 0, 1 plus h, the whole raised to 1 upon h will become e. So this will become log of e. And this can be rewritten as log of a upon log of e. Remember, the bases are right now 10, or you can take any other base. But log of a to the base to the log of e is log a to the base e, which can be written as natural log of a. So we just deduced that limit as x goes towards 0, a raised to x minus 1 the whole upon x is equal to log of a. Now remember this, we're going to use this in a moment. We are first going to find the derivative of b raised to x. Remember, calculus is all about limits and derivatives and integrations and other things. So we're going to find what is derivative of b raised to x using the first principle. And we are going to see that the number e, which we take as the base of the natural logarithm, pops up. So the function is b raised to x. So the derivative of it is limit as h tends to 0, function of x plus h minus function of x the whole upon h. We substitute limit as h tends to 0, b raised to x plus h minus b raised to x the whole upon h. We can split this x plus h as b raised to x multiplied by b raised to h. Then we can take b raised to x common, and it will become b raised to h minus 1 the whole upon h. Then we can bring this b raised to x outside because that is independent of h, and it will become b raised to x limit of as h tends to 0, b raised to h minus 1 the whole upon h. But just now we saw that limit of a raised to h minus 1 the whole upon h was log a, natural log of a. Similarly, b raised to h minus 1 the whole upon h, where h is going towards 0, will be log of b. So the derivative of b raised to x is nothing but b raised to x natural log of b. So in order to find the derivatives of such exponential functions, the natural log comes up. And when b is equal to e, we substitute e instead of b. The function becomes e raised to x instead of b raised to x. And the derivative of that function will be e raised to x into log of e. And we know log of e is 1. So the derivative of e raised to x will become e raised to x. So e raised to x is a special function where the derivative of it is itself. So e therefore becomes a very, very important number. And remember, the inverse of e raised to x is nothing but the logarithm of x, the natural log of x. We are now going to find the derivative of log of x to the base b using the first principle. So the function is log x to the base, any base b right now. So the derivative of it using the first principle is represented by this formula. We substitute, we write the log of x plus h to the base b minus log of x to the base b the whole upon h. Now log of x plus h minus log of x to the same base can be written as log of x plus h. Now instead of this minus, we can write a divide by h to the base b the whole upon h, where h goes increasingly towards 0. Now x upon x and plus h upon x can be split up, and x upon x is equal to 1, and the whole upon h can be taken out as 1 upon h. Now we do a certain manipulation over here. So instead of writing 1 upon h, we are writing it as 1 upon x into x upon h. So you can see we multiplied and divided in x over here, and the remaining same thing as it is. So why did we do this? Because x upon h is the multiplicative inverse or the reciprocal of h upon x. And anything written just before log can be taken as the power. So it becomes 1 upon x limit of h tends to 0 log of 1 plus h upon x the whole raised to x upon h. Remember, we have taken any particular base b. So we can take this log b also outside because that is independent of h. So we have this from the previous slide. As h goes increasingly towards 0, h upon x will also go increasingly towards 0 because x is a fixed number, a very small number, but the reciprocal will go towards infinity. So this portion over here is nothing but e, and we have 1 upon x log e to the base b. Now we can write log e to the base b as log e upon log b, and we are taking common logarithms as if to assume that we should have taken common logarithms in calculus. We can rewrite this as 1 upon log b to the log e, and 1 upon x into, now log b upon log e can be written as log b to the base e, and log b to the base e is nothing but the natural log of b. So we just got that the derivative of log of x to any base b is 1 upon natural log of b into 1 upon x. So this b is the remainder. It remains behind. It is the residue. It does not go off. So this function is not totally independent of this b. B remains behind. So when we take the base as e, which we wanted to prove that e should be the base of natural logarithm. So suddenly log of e becomes 1, and we get the derivative of log x is equal to 1 upon x without any residue. So since the derivative of natural log of x is 1 upon x without any residue, this brings us to our main question. What is the integral of 1 upon x dx? So we can say from looking over here that the answer is natural log of x plus c. So you saw that while taking the derivative of b raised to x or a raised to x exponential functions, and while taking the derivative of logarithmic functions, we come up with a base e because of that continuous compounding. So we saw that even in continuous compounding when the growth takes place continuously, we have this e in the formula. And even in the normal distribution with zero mean and a unit standard deviation, which is known as the standard normal distribution, the probability density function is represented by this formula, which also has an e inside. So this number e keeps on appearing everywhere and not 10. So that is why the base for natural logarithms is e and not 10. I hope you understood this. Thank you for watching.